Okay, so now that we're recording, we were talking about a question from last week's mission regarding.
Right, question 20.
Pull that off. This is for mission 4, correct?
5. Mission 5. Simple linear regression.
Right. Okay, so here we go. So can you see the question here?
Yep. I mean, residuals are positive and negative, right? When you get your regression line, it's optimized so that there's about the same amount of errors on both sides, positive and negative.
Yeah, that's correct. So
which means if you take the mean or average of the residuals, it should equal 0, approximately.
Correct.
The answer, though, that was the correct answer was the fourth bullet point that said squaring the residuals makes them, sorry, not that one, squaring the first one, actually. Okay, for me, it was the fourth one. Squaring the residuals makes them positive, so we can calculate an average as the answer to why might you want to square the residuals before taking an average. But if you square them all and they'll all be positive and you add them together and take an average of them, it's not going to be 0. It's going to be some positive number, right? So I didn't quite understand that. Do you understand that? What
yeah,
I'm,
no,
yeah.
I do understand what you're saying. So, so here, and I'm just going to pull up the lecture slides as well, so we can take a look
Okay.
at them currently. But so you're absolutely right. So the answer is that the average of the residuals will be 0, and that represents an ideal linear regression model because that means that it's a good fit for your data.
Okay.
And like you were saying, the positive and the negative residuals will cancel each other out. And then the question regarding squaring the residuals before taking an average, this is specifically in regards to the sum of the squared errors, the SSE. So this is just a way of determining how good of a fit your model is. And let me just pull up the lecture slides so that we can take a look at this concurrently.
Okay, so the second half of the question related to the SSE calculation.
Right. So it's the method of least squares.
Right. Okay.
Squaring the sum of the squared errors.
Right. Well, just based on the wording, that had to be the right answer because squaring residuals does not make them negative. So there's no way that that could have been the right answer. I just didn't understand. I thought it was saying if you take those residuals that cancel each other out and squared them and then add them together, your average would still be 0. But it's actually talking about two different things.
Right, and I can see where the confusion might come into play. I think I'll speak to the other.
So I guess the question really is, why might you want to square the residuals before calculating the SSE?
Right, correct. Well, so if you did not square them, then you would end up with 0, right? So the
Yep.
squaring it for the SSE is because then we can actually have.
Right. That makes sense.
And let me just pull up the relevant lecture slides. You should be able to see this. So this is the method of least squares. This is basically the theory behind how linear regression works, and what basically your calculator, your R program is actually doing when you're running a regression model. It's basically trying to find the line that leads to linear regression that has the least squares, right? So that it's the best fitting regression model. So it's basically running all these different calculations, and it's coming up with this method of least squares. So we have values b0, b0, and b1, the slope and the intercept of the line. And we're going to make sure that the sum of all the squared errors is as small as possible.
So it's really not an average, it's a sum of the errors.
Correct. Yeah, you're adding them all.
So probably that question should be worded, why would you want to square them in order to calculate the sum, not in order to calculate the average? Anyway, in the question.
Yeah. There's also another term, MSE, which is the mean squared errors. And let me just see.
Maybe that's what it's referring to.
That comes up in the slide.
Okay.
Okay, so let's just take a look. So here's the formula for the sum of the squared errors. And as it's saying, we typically want a relatively small SSE, so it's as close to 0 as possible. And so this is the method of calculating your different residuals, and then summing up and to get the sum of the squared errors. So here we can see these are the residuals that you have both positive and negative data points here for residual values. So what we do is we square them all to get positive values. Now we can actually add all those up to get the sum of the squared errors. So here you can see it's just summing up all the squared residuals, literally the sum of the squared errors. This will calculate the SSE, which in this case is 11.7. And as we said, we want it to be as close to 0 as possible to have the best regression line. So the whole...
Right, but that's not a mean or an average. That's just the sum of all the errors which have been squared.
Yeah, so this is the sum of the squared errors, the SSE, which is just simply a sum of them. It is not an average. There is another calculation which is called MSE, mean squared errors, which would be the average of that. They're actually giving you, it's giving you the same information. It's just going to be dividing it over the amount of data points, and to give you an idea of it spread over the data points within the...
Right. Okay.
So we could take a look. So is that clear?
Yep.
Okay, great. And sorry if the wording was a little bit confusing on that question. I can have us take a look at the wording and see if we can reword it.
Okay. Yeah. Otherwise, there was the material is very clear. So actually, if you have another minute or two, there was, I think, one other thing I noticed when it talked about tending toward the regressing toward the mean.
Yeah.
The example about with height, right? It mentioned that tall parents, the expected height of a child would be a little bit less than that, right? But then in the data that was analyzed, it showed also that for short parents, the child expected, amount was going to be also less than the parents. But according to the theory, it should be a little bit more if you're talking about small parents, right?
Right.
So the actual data example that was given seemed to contradict the theory of regressing toward the mean. But it wasn't the lecture didn't say anything about that. It just kind of presented it as an example of,
Yeah.
so if you
Take a look at this.
so if you look at the short parents, right, they have a height of 66 inches, and then you look at the short children have expected mean height of 64. Well, 64 is less than 66, but according to this theory, the way it was described, if you have short parents, the children will be a little bit taller, because that's more toward the kind of the mean of all people. And if you have very tall parents, the children will be expect to be a little bit less, a little bit shorter. So,
right. So I guess what we're seeing here, right, is that so first of all, we can try to estimate where the mean is. If we have the data set, we could actually calculate exactly what the mean is. But if we just look graphically, we probably say the mean is around here in the middle of the data.
mhm.
So the idea would be, and we could just guesstimate what this is, right? This is about 66 inches or so. So that would be the mean mid-parent height and the height of the child. So that point being is anything higher than that, as far as the mid-parent height would be, we're saying that would actually regress. So they'd be taller, but just not as tall as the parents. So it'd be regressing towards the mean to the left, shift to the left here. And if you had shorter parents, you'd actually see.
Well, that's what I'm saying. You'd expect them to be a little bit higher
Right.
than the parents, but in the actual example given, it shows a height for the children that's shorter than their short parents, which
Right.
didn't seem to agree with the theory.
Right.
So maybe that's just a mistake, a typo or something.
Yeah, no, you're actually absolutely right. Well, let's look at the regression formula. So the regression formula here says that we have an intercept of 22.38, and the slope is 0.65, right? So that's saying for every 1 inch increase in the parent's height, the expected mean height of children increases by only 0.65 inches, right? So it's exactly what you're describing. So it might not necessarily in this case be a regression towards the mean, but it's actually describing a trend where the children are actually going to be shorter than their parents.
Okay, which is just based on the slope.
Yeah, which we could look at the slope.
Yeah.
A good practice is even just looking at the slope, is looking at this formula here and describing this in words. So we could say here that for every 1 inch increase in the parent's height, which is this x value, the children's height is expected to increase by 0.64 inches.
Right.
So maybe not necessarily a regression towards a mean, but it's a regression towards mediocrity. Is kind of our conclusion.
Mm-hmm. Meaning it'll be something different than the parents. You're not going to expect them to be the same height.
Right. Correct. Yeah, so exactly right. So actually, the conclusion is that we're not able to replicate Galton's theory, right? So that's,
mm-hmm. Not exactly. Yeah.
Does that make a little bit more sense now?
Yeah, but it was a great example explaining where the term came from. So that was very interesting.
Great. Does that make a little bit more sense now that we've worked through that example?
Mm-hmm.
So for something like this, I'd say main takeaways are you should be able to read this kind of a formula. You could also do projection. So I can give you a value for the mid-parent's height, and I can ask you to calculate what the expected height of the child is. So we would expect you to know how to do that.
Right.
And that's just simply entering the value here for your x value, and then calculating what your corresponding y value would be.
Yep.
And then you should also be able to know that this is representative of the intercept, which is where that regression line will, if you plug in 0, that's where it's going to hit the y-axis. And this is your slope here. So this is for every unit value increase in x, you're seeing a corresponding increase in y. So
Right.
that's our main takeaways.
Okay. I think that was all the questions I had.
Okay, great. And just to recap what we spoke about earlier, James was asking about the final project, if we should start working on the final project, and my answer was that students are starting to begin to brainstorm about the final project, thinking about what kind of data set they want to use and what kind of analysis they're thinking about running. But insofar as actually conducting analysis, I'd say that you are still learning about these different statistical tests. So you do have time before the final project is due. That's due 1 week before the final exam, towards the end of the semester. So I'd say it's a good time to start maybe brainstorming about what kind of data set you want to use and what your kind of research questions are. But you do have plenty of time to work on that analysis. And I just want to just take a moment just to go over the calendar where we are in the class.
Okay, sure.
So today is March 8th. So the next lecture was released today. But that being said, next week is actually spring break at the university. So actually classes are not held next week, and we are actually going to release a practice exam for you to practice the midterm, which will emulate what the actual midterm will be like, which you'll take 1 week later on the 22nd. So on the 15th, you'll be able to log on and take a practice exam, which will be the same conditions that you'll have during the main exam. And just understand that practice exam is it's not graded. It's not going to affect your grade either way. It's more for you to practice test condition, and also we highly recommend that you do use this practice exam because if you have any issues with it, technically speaking, this is a great opportunity to correct those issues before you sit down and take the actual exam, because we don't want there to be any issues, technical issues while you're taking the exam. So it's good to find out earlier if your computer is not working or you're having some issues with Canvas and you need to address that. You'll have a full week to figure that out.
Okay. Is the midterm exam just that one day that you have to take it on exactly on the 22nd, or is it you can take it anytime during that week, starting on the 22nd?
So we typically release the midterm, and we do give a period for people to take the exam. I'm actually not sure if it's an entire week. It might be over the span of more like days, just because we do have students all over the world, and they're going to be taking it at different times. But we do allow for that. But I don't believe it's a full week period. But we're going to release more details for that as we get closer. And I just want to remind everyone that this week's material, which was just released today, will not be covered on the midterm. So just bear that in mind. This week's material that was just released today will not be covered on the midterm.
Okay, great. Thank you, Justin.
Yeah, of course. Pedro, did you have any questions?
I'm always wrong. Who's the one?
And James, if you had any other questions or would like to cover anything else, I'm happy to go over that as well.
Yeah, nothing further at this point. Yeah, I think I may actually just drop off now.
Yeah, of course.
And but thank you very much.
Yeah, anytime, and best of luck. Enjoy your spring break, and
Thanks.
the practice exam next week. And let us know if you have any other questions.
Okay. Thank you, Justin. Okay. Bye-bye.
I can remember exactly. She's not as bad as you think. Oh, she knows. That's because you know.